Thank you. So I'm going to talk about lower bounds for polynomial calculus with extension variables over finite fields. So before I get into this, here is a quick introduction to propositional proof complexity. So propositional proof complexity studies the complexity of tautological Boolean formulae in formal systems of logic. So that's broadly what we're interested in here. And more formally, a proof system is an NP verifier for the language of all tautological Boolean formulae taught. So it's like for taught we are interested in NP algorithms, and we are interested in the runtime of these NP algorithms or the certificates to be more precise. So for a formula in taught, we are interested in these proofs pi. Such that the verifier accepts pi as a valid proof for the tautology phi. Okay, so basically lengths of proofs for particular proof systems V for the language taught. Okay, so what is the polynomial calculus proof system? So here we encode the tautology as an unsatisfiable formula. So we take the negation of the tautology and we encode it as a system of polynomial equations over a field. So this system is unsatisfiable because the original formula is unsatisfiable. And given this system, we are interested in deriving a contradiction. So this was mentioned in the earlier talk. So given this system, we have two rules so one of the rules is we can derive a linear combination of two lines to derive a new line, or we can multiply a line by a variable to derive a new line. So with these two rules, we want to derive a contradiction, and all these steps together would comprise of a proof of unsatisfiability of the original formula in polynomial calculus. Okay, so we are essentially working in the ideal generated by these polynomials, or what they called in the original paper the pseudo ideal generated by these polynomials, because we usually limit this ideal search up to certain degree d. Okay, you'll see why. So the degree is one of the measures of complexity of the proof. So essentially, when you have the whole proof, what is the degree of the highest degree of the polynomial, any line of the proof. And also another measure is the total size of the proof. So how many monomials you have in the entire proof. So these two are two complexity measures of a proof. And so let's jump into how to get lower bounds for PC. This is obtained, as Adrian mentioned before, through a size degree trade-off. So this is the following size degree trade-off. Given a PC proof of size S of a formula F, we can show that there exists a PC proof of degree D equals square root n log S. And as he also mentioned, this requires that we are working with Boolean variables x1 to xn. So each xi is going to be taking values in 0, 1, and this is really central to our work here. So we should keep this in mind. So therefore, through this connection of the size degree trade-off, linear degree lower bounds translate to exponential size lower bounds. Okay, so basically, if you invert this function you prove a linear degree lower bound for a tautology, you get an exponential size lower bound. Okay, let's actually delve into the proof of this size degree trade-off. It's actually a pretty simple proof, and it's going to be also important for the proof of our results. So given again a PC proof of size S, there exists a proof of square root n log S, and the main idea here is that PC allows us to branch on the value of a variable xi. So what do I mean by that? So suppose you are interested in a proof of a formula of degree D, right? Then it's enough to obtain a proof of f at x equal to 0 of degree D minus 1, and a proof of f at x equals 1 of degree D, So polynomial calculus allows us to combine these two proofs into a proof of f of degree d. Okay, so basically you can pick any variable and say, okay, set it to 0. What is the degree of the proof I can get here, and set it to 1. What is the degree of the proof I can get there? And once you have these two proofs, you can say, okay, either x equal to 0 or is equal to 1. So I can combine these two proofs into a bigger proof of f of not much larger degree than these branches. Okay. So how do we use this to get the size degree trade-off? So given a PC refutation of size s, let a fat term be of a degree more than d. By the pigeonhole principle, by an averaging argument, there exists a variable appearing in at least a d by n fraction of fat terms, right? Because in each fat term there are d variables appearing, but in total there are only n variables. So there has to be a variable appearing in a d by n fraction of all of these high degree terms. Okay, and what we do is we simply branch on this the value of this variable. So suppose so we start with a proof of f of with the s fat terms. Then when we branch on this popular variable, what we call a popular variable, by which we mean exactly this, that it's appearing in a lot of terms. So suppose we set this variable to 0, then we have a proof of f with 1 minus d over n times s fat terms, because this variable is so popular that it appeared in a lot of these fat terms, and setting it to 0 killed all those terms, and we are left with the proof with a smaller number of fat terms. And we can, in the other branch we set it to 1, and this does not kill any fat terms, but now we are working with one less variable, so we can sort of use induction. So it doesn't hurt to work with one less variable. So and now by induction of this statement of the size degree trade-off, on this left branch we get a proof of degree d minus 1. If you choose the parameters d and s right, then this 1 minus d over n times s size corresponds to a degree d minus 1. And so on the right hand side you get a proof of degree d, because it's just the same size, same number of fat terms. So, and now we can combine these two branches like I mentioned before in order to get proof of the original formula of degree d. So this is how the size degree trade-off works. Okay, and so now I'll mention some explicit lower bounds for polynomial calculus. So degree lower bounds are known for polynomial calculus for the pigeonhole principle by Rasborov, and for certain tautologies by Bus, Grigoriev, Impagliaso, and Pitarsi. And so these give naturally exponential size lower bounds in most cases, because if the degree lower bound is strong enough, you get size lower bounds immediately. But now let's look beyond PC, right? So it's well and good that we have lower bounds for PC, and the lower bounds for PC are well understood over these 0, 1 valued variables, and we know we have this size degree connection, and we have good degree lower bounds. So it's time to look beyond that. And so one of the main reasons PC was introduced was actually to prove lower bounds for this system AC0P Frege, which is this system which is which consists of constant depth formulae with mod P gates as lines of the proof. So each line of the proof is a constant depth formula which can include mod P gates. And because what happened during the time when PC and the other algebraic proof system Nullstellensatz and Zatz, when they were introduced, was that we had lower bounds for AC0 Frege. So they were proved not much after lower bounds for AC0 circuits. And then we also have lower bounds for AC0P circuits, but the analogous proof system didn't have lower bounds. The analogous proof system for AC0P circuits, which is AC0P Frege, it didn't have lower bounds. And if you actually look at the proof of AC0P circuit lower bounds, it goes through these algebraic methods where they show that, so Rasborov and Smolensky, they show that an AC0P circuit can be approximated by a low degree polynomial, and a parity gate cannot be approximated by a low degree polynomial over FP. Then this motivated defining these algebraic proof systems, because we had no understanding of AC0P Frege, but we knew that there was something algebraic going on with AC0P circuit lower bounds. So the Nullstellensatz proof system and the polynomial calculus. So one of the reasons it was introduced was to gain more insight into what happens when we use algebra in proof systems. So so since the introduction, there have been lower bounds for PC, but now we have not made progress for AC0P Frege lower bounds. So we are at a sort of a standstill. So I'll go into the reasons for that. So these lower bounds don't translate to AC0P Frege due to various reasons, and so these are the reasons. So recall that this size degree trade-off depends on the fact that we are working over 0, 1 valued variables. So we took a variable which appeared a lot and we set it to 0, and we killed a lot of high degree terms, and that was essential to shrink the size of the size of high degree terms and to go into a low degree proof. So it's a very key aspect is working over 0, 1 valued variables, and this approach does not work for AC0P Frege because mod P gates are immune to such restrictions. We know this very well. Even in the circuit world, we know that parity is immune to random restrictions. So in particular, you can restrict if you have a mod P gate in your proof or your circuit, you can restrict it to anything you want, but it won't budge. So so this restriction type thing that works over Boolean variables doesn't work here. So therefore we need to look at PC-like proof systems, because we understand PC well, but we don't understand AC0P Frege too well. So maybe move towards AC0P Frege, we need to look at PC-like systems that do something that AC0P Frege does, right? So so far it's these random restriction like arguments were enough, but we want to look at a stronger system than PC, but maybe it's still easy enough to handle than AC0P Frege. Okay, so the simplest such system for which the size degree approach doesn't work is PC over -1 valued variables. So this was again a feature of the previous talk, where these tensors and these equations they are over -1 valued variables, and they're encoding the parity equations, and they are not over 0, 1 valued variables. So in general, if you consider tautologies over -1 valued variables, we don't have a size degree connection here, again because of the things I mentioned before. So over this basis, so there is no size degree trade-off, but more than that, there is also a counter example that we have these cite-in tautologies, or you can take these sort of random XOR equations. So these equations, they require high degree proofs, PC proofs, because degree measure won't change when you change from 0, 1 to -1, right? Because it's a linear transformation. So so the degree lower bounds would still hold. So this requires high degree. This requires high degree PC proofs, but has small sized PC proofs over ±1. Okay, so
this is a good counter example, because what we can do is we can efficiently simulate Gaussian elimination over -1 basis. So for that reason, even though the degree blows up, Gaussian elimination is a polynomial time procedure, so the proof length is polynomial, and so this has high degree proofs but requires small sized proofs over ±1. So so this can be kind of viewed as a weak, morally it can be viewed as a subsystem of AC02 Frege, because we are computing parity gates here, right? And but also we can view this as basically this change of basis, where suppose you're given this tautologies over 0, 1 valued variables, but you're given this additional power that you can introduce new variables yi, which basically translate from a 0, 1 basis to a ±1 basis. So basically within PC you do a change of basis, and so you can also view it as this kind of a system where you're allowed to do a change of basis before you work on the tautology. So for such change of basis, basically we don't have size lower bounds. So the moral here is that PC lower bounds are not robust even to a small change of basis. Okay, which is taking 0, 1 to -1, 1. So this brings us to the work of Sokolov in 2020, where he proved lower bounds for PC over the -1, 1 basis. So just assuming that we start with the -1, 1 basis, he showed he showed size lower bounds for -1, 1 basis, and he introduced this new measure called quadratic degree, and the new operation called split, which reduces a small sized proof to that of a small quadratic degree proof. So instead of a size degree trade-off, he gave a size quadratic degree trade-off, but not a general one, because we have a counter example here. But he gave a size quadratic degree trade-off for a specific formula, and then he showed that also quadratic degree, if you have a low quadratic degree proof, then it can be converted into a low degree proof. So that gave an indirect size degree trade-off for specific formulae. Okay, so he introduced this new notion, first of all, of quadratic degree, and he showed how to lower that using this operation which he called split. And then he also showed that once we lower quadratic degree, that is enough, because that can be converted to a low degree proof, but only for this quadratic degree and size trade-off works for only for specific formulae, not for general formulae. Otherwise, we would have a general size degree trade-off. Okay. So this brings us to our result, which is basically we show these highly robust PC lower bounds. So we show that there exists unsatisfiable systems over n log n variables of degree order log n, such that any PC refutation over FP with the subquadratic number of extension variables, basically basically with the subquadratic number of extension variables, so that means you can do a change of basis where you can introduce up to n squared many or little of n squared many new variables, and and each variable can depend on the original variables, or on at most order log n of the original variables. And we showed that any such polynomial calculus refutation requires exponential size. Okay, so again I'll review that. So you can use a subquadratic number of new variables to change your basis, and then so each such variable should only depend on order log n original variables, and this we showed that it requires exponential size for some particular tautology. Okay, so and there is some trade-offs here for the lower bound strength and these other parameters we can trade. So okay.
So I'll quickly go over a sketch of our lower bound. Uh, so our lower bound largely follows the approach of Sokolov. Uh, so we define a more general notion of quadratic degree for more general extension variables, and we also generalize this operation split to reduce quadratic degree of the proof, and we ultimately we end up giving a size quadratic degree trade-off similar to Sokolov. Okay, so so so. Uh, so in our setting, we have to work with two kinds of variables basically. Uh, Ones that take the value 0 and the ones that do not take the value 0, right? Because this is a key difference because of, again, if the variable can take a value 0, you can set it to 0 and kill high degree terms. So we have to deal with those separately from those that cannot take value 0. And for this, what we call singular variables which take the value 0, we can more or less use the 0-1 approach. But for these non-singular variables, we have to use this quadratic degree and this operation split, which we are built upon those introduced by Sokolov. So I'll just quickly go over this new definition of quadratic degree. So quadratic degree is basically, so for singular variables which take value 0, it's identical to the usual degree. But for variables that don't take the value 0, it's basically a symmetric difference. So suppose you have a term t1 z to the a and t2 z to the b, then z contributes to the quadratic degree between these two terms if and only if a is not equal to b. So it's the number of variables that are raised to different exponents in a pair of terms. Okay, so it's defined over pairs of terms, and you take a pair and you see how many variables are raised to different exponents, and that is basically the definition of quadratic degree, and this is built upon what Sokolov introduced. Okay, and so the split operation, so I won't go into too much detail about the definition, but this split operation basically tries to separate two indices of a variable z. So suppose you have a proof line which is pl z to the l plus pl minus 1 z to the l minus 1 and so on up to p1z and p0. Then this split operation tries to separate two indices I and j that z is raised to, so that once we split, we get two lines r0 and r1, which are basically r0 does not contain the exponent l0 and r1 does not contain the exponent l1. Okay, so how we do this is we evaluate this line p at two values a and b, and such that these values are carefully chosen such that these two powers L0 and L1 are linearly independent over these two values a and b, and so we evaluate the line, and we get two equations for these two values, and we solve those equations for z to the L0 and z to the L1, we solve it for R0 and R1, and we define the split to be this pair of polynomials R0 and R1. And we show that when this precondition is satisfied, that the axioms are all free of z, except for this axiom z minus a, z minus b equal to 0. So when this precondition is satisfied, we show that split is a valid refutation. Okay, and I'm out of time.
1 minute excluding questions.
Okay. Our tautology, so I'll just quickly mention what our tautology looks like. So since we have to, this split has this precondition that we have to get rid of all the axioms
containing Z, except for this particular axiom. Our tautology looks like this, where we have these parity equations on the left and we have these pigeon variables on the right, and these pigeons are selecting a subset of hard parity equations so that we can select the subset that we want basically. So if there is a variable that we want to not appear in the axioms, we just select the subset that is not a part of those where the variable is appearing. So okay, so that we do by these pigeon variables, and the axioms here are very natural. So if the pigeon selects the ith equation, then that equation must be true, and no two pigeons should clash basically. So this is our tautology, and so I have a sketch of the lower bound, which is a more detailed sketch, but yeah, I don't know if I'm out of time, I'll stop here. No.
What else? You have one sentence.
So just a sketch of the size quadratic degree trade-off. So we start with a small proof of our tautology, and so again, similar to the 0-1 size degree trade-off, we pick a variable z which contributes to many high quadratic degree pairs, and if the variable is singular, we set it to 0 and we clean up our tautology. Basically, all the affected axioms that are affected by the assignment, we exclude them and we select a subset of equations that are not untouched by this applying this assignment through the pigeon structure that we have. And if it's not singular, then we pick two exponents that are contributing a lot to high quadratic degree, and we find two values that can separate these two exponents, and we restrict basically this extension axiom to take only these two values, and then we clean up, and then finally we apply split. Like here there is a small case analysis, but I'll ignore that, and we apply split to basically separate these two exponents I and j through these values a and b. Okay, so and so you just repeat this until you have a low quadratic degree proof, and then switch to a low degree proof using Sokolov's argument. Then that gives a contradiction. Okay.
Thank you. Just a quick question.
Yes.
You have this nice presentation with the fictional principle of attached terms.
Yeah.
The question is it logical to think that for the Sasank formula that happens as well?
No, yeah. So the pigeonhole principle there was not the tautology. It was the fact that there exists a variable that appears in a lot of fat terms. That is by pigeonhole principle. So it works for any tautology. Yeah.
Okay.
Yeah.
Another question. Yeah, I have just one question.
Yeah.
You had a slide about, and you said that you take this, you have some condition for
Yeah.
applying this z
Yeah.
variable where z minus b or times z minus a,
Yeah.
only if it exists in this form.
Yeah.
But why would it, maybe all of the z's, all of the extension variables do not exist in this form?
Yeah, so maybe I can draw a quick picture. So basically you have the axioms, right? And you have some axioms that have z. First we use the structure of our tautology to get rid of these axioms. So we have these pigeons and the equation kind of thing, right? So we use that structure to get rid of these axioms. Then once we are rid of these axioms, and then we only have the extension axiom itself, like this we cannot get rid of. So this we restrict it to something like z times so basically this we restrict it to z minus a, z minus b through a series of operations here.
Yeah.
So if z or so the main issue here is this q, right? Like where if this is the defining extension axiom for z, then this q can contain some variables x1 to xk, and these x1 to xk can appear here.
Yeah.
So but our pigeon structure that we have, we deselect these where these axioms. So
Okay,
we
yeah.
get rid of them. So then this is the only axiom. And
Yeah, I got it. Yeah. Well, let's thank